All right. Hello, everyone. Welcome to the Wisconsin Robotics Seminar Series. It's my pleasure today to introduce speaker Kris Hauser, who is a professor of computer science at the University of Illinois at Urbana-Champaign. Kris has been working on very interesting problems and generally in real-world robotic manipulation and control. A lot of times our work at Wisconsin overlaps with Kris's, and we find inspiration from each other's work. Without further ado, I really look forward to seeing Kris's talk.
Thank you so much, Bill Gay. I'm really pleased to be here. This is a little bit of a strange experience being virtual still. It would have been great to attend in person, but I guess, we're kind of in this hybrid world right now. I'm right now talking to a blank screen, which is another very strange experience. I can't see any of you or see any of the Q&A or chat. And so hopefully Bill Gay will be able to raise questions if you have any that seem pressing. So in any case, let me go ahead and get started. I'll be talking today about some of the work that we've been doing in my lab for the last couple of years, a topic that I have really become very excited about, which is open world robotics. One of the reasons why I'm so interested in that is that, the robotics field has matured quite a bit in the last, in the last 5 years or so. We have essentially seen massive investment into autonomous driving and other kinds of fields in robotics. And I can kind of outline the two general frontiers of robotics as being one in which safety and reliability is paramount. And there are lots of data available, a fair degree of structure. For example, in industrial robots, there's a huge amount of structure. And autonomous driving, there's quite a bit of structure in terms of the driving environment, and also surgery and other medical robots, which are at the forefront of robotics, do have still quite a bit of available data on how humans and bodies kind of interact with tools, and the structure of a human body gives you a fairly confined environment to work in. However, there's very little room for error, and you have to essentially perfect the autonomy for you to be able to make progress in these domains. And in another general direction, there are problems in which there are very little data and structure, yet we still have some room for error. And the robot has the ability to use this room for error to, by itself, autonomously improve its understanding of how it interacts with the environment. So for example, in service robots in the home or medical kind of tasks in, for example, hospitals for nursing and elder care, also extraterrestrial exploration, we have these problems in which it's almost impossible for us to build, let's say, a company that will spend, let's say, $1 billion to try to optimize for a single environment. We actually have to have the robot adapt to its environment during deployment time. So this difference between the development phase of a robot and the deployment phase of a robot is also known as the deployment gap. And when there is a deployment gap, we need to start thinking about the problem of open world robotics, which is when the robot itself has to adapt to its deployed environment, and we don't have information about what that environment is going to be like during development time. We can't test on every single person's house in advance before we sell this robot. I do some work on the kind of more reliability to the side. So we've been working on some industrial robots and manipulation, as Bill Gay mentioned in his introduction. So as an example, we've worked on packing. This was sponsored by Amazon, which of course wants to ship billions of packages daily. This is a packing problem in which we're trying to address very challenging real-world packing problems, and we optimize the packing plans using feedback and advanced planning. So in this case, we're able to achieve high reliability rates. However, I'm also very interested in open world problems as well. So just a little bit more information about what we mean by open world problems. This was developed in the AI field. So essentially a kind of statement of open world AI is as follows. So if we want to deploy AI successfully in the real world and not just on data sets, we need to be able to drastically adapt to different domains. And we have to accommodate this domain gap. In robotics, it's similar, although it's that if we're trying to deploy robots successfully in the real world and not just our lab, we have to address the domain gap. So this domain gap means that during development time, We have some sets of objects or environments that we're able to train on or develop on, but then at deployment time, we're now encountering new instances of different types of objects, either different shapes or completely different classes of objects than we've ever seen before. Now, we may need to acknowledge a few things. So open world AI is a very broad field. So there's lots of different types of techniques that are investigated along this flavor, but it's more of an acknowledgement that we need to specifically address this domain gap. It's not just a sort of side effect of the work that we do. It's not just, let's say, standard machine learning, as hopefully most of you out there know the kind of basic workflows of machine learning. You have a training set, testing set, and voila, things work. If you're not so familiar with it, I'll give a kind of whirlwind introduction of it. But the domain gap is an incredibly important roadblock to the success of AI in many areas. And we need to explicitly study how methods generalize across large domain gaps. Right? We need to actually explicitly, as a subject of our study, try to understand how well our algorithms are able to hop from a different training domain to the deployment domain. Moreover, we can develop methods that explicitly target these domain gaps, and these tend to deploy more successfully than those who do not. So for example, adaptation is an incredibly important topic. How do we adapt our models using, let's say, meta learning or few-shot learning or transfer learning so that the information that we get during deployment helps us improve our performance during later deployments? So we kind of use the kind of, as I said before, the room for error at the beginning to then improve ourselves and get better. I will also say that robotics is a bit of a late comer to this acknowledgement. Open world AI as a term has been around for at least a decade or so, but we need to start catching up to the AI, ML, and vision fields. And some of the folks who do robot learning have already been working on this for several years, but we do need to, I guess, get the word out to the vast majority of roboticists who are still stuck in kind of an old closed world kind of environment or mindset. So just a little bit more theoretically, what the problem is that's posed by the domain gap is that, in standard machine learning, you tend to have some sort of training data in some sort of space, and I'm illustrating just abstractly some kind of classification problem. We're trying to separate the red from the green. These data are distributed according to some training distribution, which is marked by this kind of cloud over here. And when we go and try to train some sort of, let's say, classifier, or you could also be looking at regression problems, but here I'll just say classification. We want to look at the classification boundary, and there's actually many classification boundaries that are consistent with this data. So the question of whether we want to output something like this or like this is governed by our performance on a testing set. Right? So in standard machine learning, the one that I grew up learning in graduate school, was to assume that you had testing data that was IID, independently identically distributed, from the same distribution as your training set. And so if you have better performance on your testing set, that's great. You use that classifier. Right? So we want to use this, this solid line over here because it has better error, lower error on the testing set. Now, what happens?
Kris, there's a quick question here. Are the object labels assumed to be all known?
So in, well, I guess in traditional supervised learning, yes, there's lots of variations of learning, but yeah, I'll talk a little bit about the unsupervised and semi-supervised cases too.
Great, thank you.
Thank you. So in the open world setting, there's this domain gap problem in which the test distribution is unknown. It's likely different from the training distribution, and we oftentimes have some lack of ground truth, or it's very sparse. So for example, when we deploy a robot to a new environment, maybe we can afford to label a couple of things in our environment, maybe a couple of times, but we will expect the robot to be able to then adapt and understand what that thing is and identify it with high confidence in the future. We don't want to have billions of instances of training data for that single class, or even hundreds. We want to get down to a handful or a dozen. And so we may be able to, let's say, capture a lot of unlabeled data, a small amount of labeled data, or sometimes just no labeled data at all. So there's many different ways of trying to address this domain gap problem. One of them is called transfer learning, where we try to account for distribution shift in these predictions. One method that's completely unsupervised is called unsupervised domain adaptation. And this essentially accounts for the kind of general shift of our training data to our domain data, even without labels. And we can do something like a shift of our classifier to let's say, account for this mean shift. There's a few applications of this, and for example, computer vision, and also in robotics as well. So for autonomous cars, you can try to do domain shift. You can try to adjust for domain shifts from, let's say, light to nighttime, or from let's say clear skies to precipitation. So that's one approach that could be done, but you don't have any kind of labeled data. Another approach, if you do have some labeled data, is called fine tuning. So for example, even if you did this unsupervised domain adaptation, you find that some of your predictions are wrong, you could have a small amount of annotation, perhaps by interacting with a human, and perform an approach called fine tuning, which then tries to adapt to that new information. And again, there are plenty of instances of this in computer vision, and there are also instances of this in robotics. Most significantly, or most widely known, is probably the sim to real problem. So people try to train, let's say, policies or predictors on simulated environments. And then when you try to jump to the real environment, which has different kinds of lighting conditions, different types of object shapes, and so on, you can try to retrain your classifier so that you both use the background information from the simulator while also using the much sparser labeled data from the real world. And finally, one approach that I'll discuss is meta learning. This is the idea of learning to learn. The idea is that we don't exactly know what the deployment time data is, but we want to ensure that the learning method, the pre-training method that we get, can then adapt to the new labeled data well. So in fine tuning, we're still using classical types of approaches in order to try to learn at the deployment time. Here, we're trying to do something a bit beyond that. We're trying to make sure that the secondary adaptation process works very well and generalizes well explicitly. And the weird thing about meta learning is that it requires us to take a different workflow. Rather than just having train and test, we now have to simulate. In order to train and evaluate meta learning, we have to simulate hypothetical deployments to new hypothetical domains. So we have to basically we have to synthesize domain gaps that we think will exist during deployment. So there's a few examples of this in the machine learning literature, and there's also been some work, a lot from Berkeley, for example, on using meta learning to try to improve reinforcement learning or robotics grasp planning tasks. So I think this is all great stuff, and it's really looking at things from the machine learning perspective is a great start to understanding open world robotics. However, learning is not just the only part of open world robotics that we need to care about. We need to not just be able to do a better job in learning, but we also have to do a better job of generating intelligent behavior. And I'm not really, I don't really subscribe to end-to-end reinforcement learning. If you were to do end-to-end reinforcement learning in some sort of open world fashion, open world AI fashion, you sort of then have an open world robot, but it's really not been as successful as we might want to hope for. So we really have to start thinking about how to adapt the whole autonomy pipeline. So we've got these sense, plan, act frameworks that end up needing to be adapted to this open world setting. So I'm interested in trying to get the minimum viable product for open world perception, open world planning, as well as those external interfaces that let humans annotate and interact with the models used inside the robot. So there's a lot of different things that I think would be really useful. We really need to have open world robots if we're going to be having, let's say, service robots that adapt to the home. On the top, I'm involved in this AI farms project with agricultural robots. They need to adapt to totally changing conditions that we're never seen. If we're going to train this in Illinois and deploy it, let's say, in India, you're going to have very different, let's say, dirt, weeds, other kinds of changing foliage and so on, that the robot will have to adapt to. And finally, I'll talk about some extraterrestrial exploration project that we've just started recently, where we have to send a robot to either Europa or Enceladus, and we have no idea what it's going to look like and what the terrain is going to feel like. I'll focus on a couple of things that I've been working on the last few years in my work. We've been looking at physical interaction modeling, informative path planning, and supervisory control. But these are just a small set of things that I think the world should be working on in terms of trying to accomplish open world robotics. I do have a bit of a split personality, so I do work on human-in-the-loop systems. So one of the great things about humans is that we are extremely adaptive to highly unstructured environments. If we are able to supervise the robot, we can build a semi-autonomous system in which we can watch and correct for the robot. We can teach the robot new things. So the big challenge is going to be building user interfaces to interact with autonomy. I'm also interested in open world autonomy, full autonomy, in which the application can't leverage a human, and we have to adapt from very small amounts of data. So let me start with the first side of things. So we've been working quite a bit on human-in-the-loop robots. The kind of key project here is called the TRINA project, the Tele-Robotic Intelligent Nursing Assistant. It's a semi-autonomous platform for nursing in quarantine environments and also telemedicine. Here we're basically doing this is a sort of avatar that you can log into, and you can basically control it as though it were an extension of your own body. You can see that there's a operator here in the upper left using a VR system. This is an off-the-shelf Oculus system, and he's looking around the environment, he's immersed in it, looking around. You can see the rendering from his point of view on the upper right, and basically his movements are translated essentially one-to-one on the robot. So this robot itself provides the ability to sense, act, and communicate. We are then trying to, with our more recent research, trying to assist the user as well as to automate basic functions with this kind of robot. So here's some of our teleoperation assistance work, and we also have some fully automated medical exams, which I'll talk about in just a bit. Why I'm really interested in it, let me just briefly go through a few statistics that motivate why I'm interested in telerobotics. Well, we're all working remotely, at least in the kind of information economy. We've been working remotely for several years now, and this is really changing the way that we're looking at work. So about 25 to 30% of the workforce worked remotely during COVID. Office buildings were vacant to a great extent. Many of them were actually rented, but still vacant. If you asked people to work full-time in person, a lot of home workers have adapted to this kind of mode of working, whether it's due to health reasons or because of convenience. Many people have considered quitting if asked to work full-time in person. Now, this is all great, and this has been helpful for us in the information economy, but 89% of in-person jobs can't be done from home because they involve some sort of physical interaction. You have to actually do something with your hands or feet and work in person. And not only that, we have a looming healthcare staffing crisis. So COVID has been devastating across the world, and an estimate of the number of medical personnel who have died is over 100,000 across the world. And this is as of May 2021, as estimated by the World Health Organization. And in the US, and also Canada, we are having major staffing shortages, especially in rural and remote settings. And we are projected to have a need of 200 to 450,000 new RNs in the US by 2025. And not only that, there is an aging population in the US and across the world, and we need in-home care for aging in place. People vastly prefer to age in their own homes, and we need the projection by the Bureau of Labor Statistics as 1 million new caregivers needed in the US by 2035. And this ranges anywhere from somebody to just help pick up your groceries to full-time trained medical staff working in your house. And the thing that ends up happening when you age is that you end up having this kind of transition of needs. You have you're starting out with very limited needs, maybe somebody just helping out a couple of hours a day, ranging to full-time round-the-clock care, at which point you might be moving to a nursing home. And I really believe that it's possible for technology to help help ease the transition from these low kind of resource usage settings to the very high resource usage settings. So let's say you have an older parent who needs help, let's say 5 minutes a day, but throughout the whole night, you still have to pay for in-home care across basically around the clock, right? You're not going to have somebody drive 30 minutes to grandma's house and help them at 3 a.m. and then drive back home only to be called back an hour later. Right. So this is a way for robotics and telerobotics, especially, to be able to help out. So we're able to improve flexibility in the labor market, ease the staffing crunch, reduce commute times, costs, and emissions, and allow family members to help out with elderly family members who might need help very occasionally. Not only that, our technology is getting pretty good. We've built 3 versions of our TRINA robot so far, and it's been actually remarkably successful. And the hardware is reliable, the costs are going down, the networking is getting better and better. However, we still need to achieve better reliability in system integration. We need better fine manipulation skills in telerobotics, and we also need better customizability, usability, and ergonomics. Let's see, I'm just going to kind of skip this. So our involvement in this kind of area started in 2015 when we asked the question whether we could provide physical care via a robot. This was started in the Ebola response. If you touched just a single drop of blood, you could potentially get infected and die. And so we developed this TRINA system, version 1.0. You can kind of see it's a crude version of our later telemanipulators, but we were able to show that you could do a variety of nursing tasks with the robot, including deliver food and medicine and perform some basic vital signs monitoring tasks. Of course, there's some things that the robot can't do. You'd have to actually have a human. For example, it's not going to insert an IV. It has lots of problems with fine manipulation, but for these kind of manipulation tasks, it's able to do the job. Here we had a trained operator, and we've been working towards making it easier and easier to use for a untrained operator. And so basically we're at the stage where we have this direct teleoperation interface, but we've provided enough operator assistance and immersion for novices to pick up the robot actually relatively quickly. In this kind of left side of this design philosophy spectrum, where we're looking more towards direct teleoperation of the robot, the operator completely controls the low-level motion of the robot with only minor adjustments governed by the robot controller. And our job is to try to minimize maximize the situational awareness, immersion, and transparency of the system. But one of the problems with this type of operation is that it's actually really fatiguing. So after 30 minutes of operating the robot like this, you end up getting sweaty. You feel like you've actually exerted a lot of work. And it's really not a very ergonomic and comfortable situation. And so this is why we're interested in looking at the autonomy side of this spectrum. So over on the right, you start to see greater amounts of autonomy, where full autonomy is in one corner, and it's going to be very, very difficult for us to actually achieve full autonomy in a medical setting, which is very chaotic and requires a lot of expertise. Humans have a hard time being nurses and doctors and so on. We have to train for years to get there. So instead, what we're trying to do is look at supervisory control, where the operator is designating tasks executes with low-level motion. You can either have eyes-on supervisory control, where you're watching the robot and ready to step in if things go wrong, or you can have eyes-off, where you just kind of look at the task, you kind of see what the robot's about to do, you press the button, and you can ignore it for a few minutes as it goes and completes the task. Maybe it gives you an alert on your phone saying, hey, I'm done, what's my next task? Now, one of the issues is that we have to achieve reliable autonomy and error detection, and we need to scale to lots of different autonomous primitives, as we'll see. Just a little bit about the kind of left side of this figure, the direct operation. We've been working on a lot of operator assistance, where we make the operator's job easier, handling some aspects of the motion that are hard for the user to understand. Local constrained movement, impedance control lets you act softly, contact stabilization. We're working on some local collision avoidance, but these generally help the operator's job and makes it easier for them to learn how to use the system. We've been entering our TRINA system into this ANA Avatar X Prize competition. In September last year, we had 3 tasks that needed to be performed. The judges, we didn't actually have our trained operators running the robot. We actually had to train a judge within 60 minutes of time to use the system. And the judge had to interact with what's called the recipient here, the other human, and perform these tasks on their own. The technology, like I said, is getting better and better. So it's a really hot competition right now in terms of like the top 5 teams. We're all essentially accomplishing these tasks pretty well. It's just a matter of kind of refinement and ergonomics at this point to try to improve the operator interfaces. In this semifinals, we scored 4th place, even though we had almost 100 points scored out of 100. And we're getting prepared for the finals in basically 1 month, almost exactly 1 month. And we're really at the point where we're just running the robot and trying to perfect things. So really the technology is really getting there for teleoperation. Let's see. But we're also interested in looking at autonomy. And so these tasks like, let's say, medical exam tasks, for example, auscultation, could be potentially automated with various focused effort on engineering automation techniques. So auscultation here is what everyone is basically experienced at a doctor. They use a stethoscope to listen to your heart and lung sounds. We have worked on the first automated auscultation execution that was performed last year and published in 2022 ICRA. Basically here the robot will view a human, fit a reference model, an anatomical to the scanned person, and identify landmarks that it should be scanning, it should be listening to with this digital stethoscope. Now it doesn't automatically diagnose the patient. These are basically doing recordings, but it is able to autonomously figure out whether it had a high quality recording or not. So if it was muffled or mixed with other sounds, if you're listening to the heart and you hear some breathing, it will actually adjust the position of the end effector so that it tries to get a clear sound of the target anatomy part. Now, this produced similar quality results and was faster than teleoperation by a medical student. We had a medical student also perform this task with the robot, and the robot autonomously was faster. And of course, because this takes several minutes, it would be very fatiguing for a doctor to do this every time. So basically, we can push button autonomy for some medical tasks. A bit about the kind of infrastructure for this. So when you build semi-autonomous functions onto a teleoperated robot, you have a lot more than just autonomy to think about. You also have this user interface layer that needs to interact with the autonomy guts. So we need to have these front ends, and here we're working on VR, desktop, and mobile user interfaces. We have many different types of apps that can be essentially triggered by the users in each of these interfaces, and that will trigger some of the autonomy pipeline on the robot. One of the things that we've started to as we start to develop more and more autonomous primitives is that if we're just using, for example, a menu-based user interface, as we get better at autonomy, we're going to start overloading the operator where it starts looking like an airplane cockpit. You can see up here in the upper left, you have lots of buttons, and it's not totally clear what each of them does. And for a novice user, this is actually quite overwhelming. So we've been working on trying to reduce this operator overload by providing these expert action recommenders that use the perception context of the robot, as well as the history of actions performed in the past, to suggest just a small number of actions, which tries to minimize the operator overload. We're doing this in an open world setting in which we use label-free segmentation. We have, for example, these target objects that we don't know what they are, but we know that they're there, and we know that we can kind of segment them into certain regions. And we can predict various attributes of these regions to try to predict what the user wants to do with them. We're predicting the top k most likely actions from this perceptual input, as well as the history features. And we're using expert operator data to figure out, to make the prediction of what the user would like to do next. And so we're inferring what kinds of constraints the user might want to use, or what types of snapping actions you might want to do to snap to a sort of target plane. And the the novice operator will then use the recommendations to then choose the next action. And we were able to show that with our structured action prediction framework that we were using, we achieved 90% or higher accuracy in top 5 prediction, and this is between tasks. So we trained on 2 tasks and then tested on a 3rd. So 2 of the tasks were wiping a whiteboard and unscrewing a jar, and then the test task was solving this animal puzzle, and we're able to achieve still high accuracy because there's a lot of prototypical sorts of sequences of actions that would be performed. Just in terms of the future of human in the loop open world robotics. One of the questions is whether supervisory autonomy can ever beat direct teleoperation or shared control in open worlds. So the problem with supervisory autonomy is that you have to understand the purpose of each of the actions that you then are going to be triggering. Whereas if you're doing something very immersive, you have this analogy, you have this prior training of using your own human body to be able to accomplish these tasks. So instead, this is a sort of foreign environment. We see these like buttons that we might want to press on, and then we trigger the buttons, and we hope to develop trust in the robot to be able to accomplish tasks. So far, we're not at the point where semi-autonomous operation beats direct operation for these very open world scenarios. And there will be sort of an achievement if we ever do beat it. If we ever do have a semi-autonomous robot beating direct op, this would be a semi-autonomous supremacy kind of question by analogy to this idea of quantum supremacy, when quantum computers can beat standard computers in certain tasks. And then there's the question of, can full autonomy ever be both? Can we just have a completely autonomous robot do some of these, let's say, nursing tasks? What aspects of the human interface encourages the operator to invoke these autonomous actions? How do we make them usable? How do we make them predictable? How do we get the user to trust that the robot will do what it's asked to do? And also, how do we scale these up to huge numbers of actions? As we throw more money at the problem, we'll get more and more autonomy, more and more actions. And we need to have better intelligent user interfaces to be able to let us select from those. Okay, so let me kind of switch over to from hospitals to space. We are also starting a project where we're looking at sampling extraterrestrial terrains. And if you look at the existing rovers, they are either direct teleoperated or operated with supervisory autonomy. And one of the problems that people have faced when trying to sample Mars or lunar terrain is that the properties of the terrain that you're trying to sample from may be different from what you expect. And this is not so bad when you have a human in the loop because they can make adjustments. However, NASA is working on sending landers to very, very far off moons of Jupiter and Saturn that may have the potential for extraterrestrial life, or at least the signs of extraterrestrial life. And so they need to be able to do scientific sampling missions such that the autonomy actually takes the role of the scientist. The autonomy itself has to be adaptive and figure out what to do in case something goes wrong. Sampling will need to adapt to the unexpected. So this is more of an open world autonomy problem. When we think about these extraterrestrial environments, we have satellites that are able to scan, but we only have approximately like 15 meter resolution per pixel from our closest flybys of these moons, Europa and Enceladus. And so we don't know what the low-level, the fine-grained terrain composition is actually going to look like. It could be completely flat, or in some extreme, it could look like the Chilean penitentes, which are 5-meter spikes of ice, which would definitely cause a problem in terms of landing, but also sampling. Even if the lander did survive on such a landing, you then need to adapt to the shape of that topography. The material composition is also very unknown. We don't know whether it's going to be hard ice. These moons have these ejections of water, which then turn rapidly into granular ice, and we don't know whether it sinters together back into solid ice, or whether it's kind of like grains of hail or even snow on the surface. We really are not entirely sure once we land what the terrain composition is going to look like, and we need our manipulation to be adaptive to all of those possibilities. So our project is called DRILLAWAY is to train adaptive autonomous sampling behaviors on Earth so that we hope that we can maximize scientific value when we go to the unknown. And if we have suboptimal conditions, our degradation of performance is somewhat minimal. We're opting for a few-shot learning approach in this project. We're doing some sampling of example terrains. We are trying to look at some analogous problems of scooping of different types of granular media. And we're trying to take the same kind of autonomy guts and then eventually convert it onto the final lander. But basically what we're doing is looking at the RGB images and the outcomes of scooping for various sample scoops. We have different parameters of how we scoop, how strongly we scoop, how deeply, what angle we use. And what we're trying to do is first train some base predictor to predict the expected outcomes. This would be kind of like a standard deep learning type approach. But we're also looking at the meta training of the adaptation mechanism. So once we do have a few scoops, first we start with 0 scoops, then 1 scoop, then 2 scoops, and we get to see the outcomes. We then want to adapt in case the first ones were suboptimal and then perform better on later ones. We have many different methods that we've been exploring that are few-shot learning techniques that are known in the literature. And then we have an optimizer to select a scoop that maximizes some function of the outcomes. So one question that I have asked is, could meta learning actually help here? What do we need for meta learning to actually help? So first of all, the outcomes might need to be sensitive to the observables, but we might also not rely totally strongly on those images because we have no idea what color lighting conditions we might actually have. But they must be sensitive to action choices and unobservable latent variables in order for meta learning to help. So we did verify that if you have different compositions of materials, these scooping actions, you don't really have some universally optimal scooping action. If you have sand, you deeply scoop and you stiffly control, and that maxes the volume. Whereas if you have rocks underneath the surface, if you jam down too hard, you end up getting stuck and you end up not having a very promising scoop. So here you can see that on the right video, the robot is actually jamming on the rocks underneath the surface, and it's not able to then scoop up a large volume of the sand. The latent variables, which are in this case the material composition and interaction forces, interaction physics of the material with the scoop, are latent. They can't be directly observed until you actually act on them, but they are correlated with the observables, and they're also correlated with the history of the previous outcomes. And we hope that better knowledge helps our decision maker improve our future action choices. There are some cases in which it'll just be the most pessimistic environment where we can't actually scoop anything, but in many cases, and in most cases, we can scoop something by making adjustments to our initial attempts.
Chris,
and for the adaptation.
The text started garbling. Okay, back now. Every once in a while, the text gets garbled, but then it clears out. It just cleared out. I wanted to warn you. So we're good. Yeah, go ahead.
Okay, I guess I'm getting some garbled sound too. I think it's maybe just the computer.
I think maybe your computer slowed down, or
you see everything?
Yep, I can hear you. Yep, we're good. We can see clearly now.
Okay, great.
Thank you.
All right, so we've been doing some testing of various meta learning techniques. We've been seeing some mixed results here. So we've explored various meta methods versus non-meta methods, and we have found that meta training actually does significantly improve the calibration of our kernels, whereas high capacity models actually overfit quite a bit. And so our techniques have actually been, the best techniques we've observed have used actually very shallow adaptation mechanisms while using deep kind of baseline models. And this has been the most promising thing so far. Our current experiments are ongoing, but we're really excited to share this work sometime soon, hopefully. So it will be something hot off the presses. Let's see, I guess what I will do is I'll kind of skip over this part. I wanted to talk about one thing that I found to also be very exciting about this kind of idea of open world robotics is that we not just have to open the world up to the robot adapting its autonomy, but we also have to open the world up of robotics to novices to help design robots more quickly. I'm very interested in the idea of putting tools for these more advanced functions into the hands of novices. Basically, I've seen the tremendous impact that having very easy deep learning approaches like PyTorch has had on undergrads everywhere. There's a huge interest in getting into machine learning because of the ease of these tools. And we're trying to do a similar thing for controller design. So if you look at any kind of new type of robot, whether it's a soft robot or a underwater robot or a drone, they have very unusual dynamics that have to be learned in some way, as well as using some sort of optimization-based controller to try to achieve some sort of objective. Now, There's been a huge amount of interest in using reinforcement learning to address these types of tasks. It's really great to get started. It's very easy to just download a package and connect it up to your robot. You don't need to use much domain knowledge, so you don't have to learn about robotics. You don't have to do too much hand tuning, and policy evaluation is fast. However, sample complexity tends to be very high, so if you need to gather data on the actual robot, it's extremely expensive. There's no stability guarantees, and also the exploration is unsafe. On the other hand, I like to use model predictive control because it's very explainable and transparent. We can also change our goals and constraints on the fly according to our engineered needs. However, we require accurate dynamics, and we also have very few off-the-shelf solutions for model predictive control with learned dynamics. Not only that, it's really, really laborious to hand tune these, and the performance of these controllers is extremely sensitive to the choice of dynamics model, the optimizer parameters, etc. And optimization is also computationally expensive. If you look in the world of machine learning, one of the recent trends has been to look more and more into the idea of auto machine learning. So this automatically tunes your supervised learning models in order to try to improve performance on your using cross-validation. They tend to use Bayesian optimization to explore some sort of hyperparameter space. And the thought of this project is to see whether we can do the same thing for model predictive control. We have this technique that we're very excited about called Auto MPC. The idea is that the controller tuning process is an automatic tuning process. We have a set of data that we have as an initial data set generated in a completely uninformed manner, and then we run Auto MPC. It tunes the controller, and then you get better results. So as an example, here's the sort of mean tuned controller, which kind of limps forward a bit on this half-cheetah problem, whereas the best performer does quite a bit better job and is able to achieve pretty good performance. Now, comparing this, so look at this really terrible baseline controller here, which is just doing motor babbling. If you're to try to learn using the best offline reinforcement learning technique out there, which is called VCQ, the true performance is actually quite poor. Lower here is better, and our Auto MPC controller is usually able to outperform this quite a bit. Another great thing about this package is that it's very easy to use. We have a wide variety of system ID methods, optimization methods, and objective functions. Now we have actually many different ways of handling constraints, and you can go from a data to a controller in under 30 lines of code. So if you're the type of person who might be an electrical engineer, mechanical engineer, and doesn't really want to spend a lot of time building an optimizer and doing a lot of coding for that, you can just gather data, throw your data into our black box, and then you get a controller out of it very quickly. Now, if you want to download this, you can see the link down there. We're now working on the version 0.2 of our system, which is going to have a lot more interesting kind of features to it. We've applied this to soft robots. Most recently, we submitted this to ICRA 2023 just a couple of weeks ago. We've been applying this to a soft robot arm. This is a hydraulic soft robot arm, which exhibits a lot of different complex dynamics. And we were able to show that Auto MPC achieves better multitask accuracy than either doing learned inverse kinematics or visual servoing. So you can see the error plots of the kind of targets in this sort of triangle shape using open loop IK, or approximately 2.4 centimeters in error. Visual servoing is approximately 1.4 centimeters, whereas Auto MPC is able to get less than 1/3 of a centimeter on average across the training and testing domain. We also tried out of distribution testing, and of course, with any given learning technique, there is going to be some degradation of performance. In this case, we were able to achieve about 1.5 centimeters of error in this out of distribution domain. The robot was not trained at all in tasks that were outside of this little triangle marked in gray down here. So we're quite excited about that as well. I just wanted to close off by mentioning a little bit about kind of how open world robotics changes the way that we do robotics. So if you want to look at training machine learning as an approximation of the robot development process. So with the robot, we built some algorithms, we tune parameters, we might have some machine learning going on in there. So all this kind of tuning is approximately the same as training a machine learning algorithm. If we're trying to build an open world non-adaptive system, basically what we want to do is train on some training sets, and we want to test on some testing sets. And the primary commandment of machine learning is that you don't train on your testing set. So in order to really enforce that we do this rigorously in open world robotics, is that we have certain training domains which we're allowed to tune on. We're able to kind of test our algorithms. We're able to train our machine learning algorithms or detectors and so on the training set, but we always need to kind of put a firewall between that training and the testing that we do in these representative deployment domains. Furthermore, we need to be able to test, we need to be able to control the train test domain gap. So we need to be able to say, okay, I'm going to be training on this, let's say, YCB data set for manipulation, but I'm going to be testing on, let's say, similar types of objects that have similar types of material characteristics. Or I'm going to extend to slightly deformable objects, or I'm going to extend to this. And we need to be able to clearly articulate what we mean by the domain gap and how large we think that domain gap actually is. So we need to examine the change in performance as the domain gap grows. Now, on top of this, if we have an adaptive system, we actually have to do a different type of workflow, which is even a bit more complicated. We have some training stuff, which is offline. But then what we need to do in order to evaluate performance is that we don't just test on our testing sets, but we actually have to simulate deployments. We have to say, okay, well, you're now being deployed. You're now given this much amount of time or examples in your what's called a support set. You'll perform potentially badly on that support set, but hopefully after that training, after retraining, after adapting, you're able to then test on the remaining examples, and that's called your query set in the meta learning literature. And if you test to see how well it does after adaptation, that is a more effective gauge of deployment performance. So there's a lot of complexities in this kind of workflow. First of all, you have to choose your support set sizes. How many examples are you allowing the robot to see before you start evaluating the rest of the adaptation performance? If K is small and you achieve good performance with one method versus bad performance with another method, it shows that that first method has better short-term adaptation performance. Whereas if you increase K and the other method starts to outperform it, then that second method has better long-term adaptation performance. Depending on the application, you might want to prefer one over the other. You might want to also repeat deployments, which reduces your noise. But one of the problems with this is that with robotics, experiments are expensive. And so the more repetition that we need to perform, the more complex the kind of development of our systems will actually be, and the more work we need to have to put into our papers. We need to also control our domain gaps so that we don't demoralize researchers, because if you try to do some stuff in the lab and then you try it on, let's say, a human environment, let's say you go to a hoarder's house and you're trying to clean that hoarder's house, you're just not going to be able to work. It's just not going to be able to perform very well. So we don't want to demoralize ourselves by seeing bad performance with these huge domain gaps. And we also need repeatability between labs. So we need standardized procedures, we need standardized benchmark tasks in order to make progress in a given domain. I'll close off with what I want to call the 6 commandments of open world robotics. First of all, as anyone would say in machine learning, don't train on your testing set. So you should not develop on the testing set. You need to put a firewall between yourself and the testing set. If you want to iteratively improve your behavior by looking at testing, testing-like environments, you have what's called a validation set. In this case, you have train, validate, and test. Second, oops, I have a missing and here. Okay, so you have to be very specific about your training and testing set generation process. And clarify how these are defined in your papers. This has to be a part of the research that we do. In this development, we have to justify the choice of our domain gap in some sort of verbal motivation. We have to justify that our choice of shift is representative of real world deployments. And that has to be argued with sort of our verbal language and our kind of argumentative capacity. You also have to be very careful when developing these adaptive techniques, such that you don't leak information between your simulated deployment to the next deployment. Right after every simulated deployment, you have to reset the information state back to offline, the offline training state. And this is somewhat of a bit of a way for people to cheat, but we have to be very careful about avoiding that type of cheating behavior. There's one more here. So finally, if you're working with humans at all, you should not forget the role of the human. And we need to be involving human subject studies if we're involving any kind of human teaching or human training, or we can also develop protocols for simulated humans that we can then try to replicate with our own staff, or also to simulate it in silico. And groups of communities, whether you're doing manipulation or whether you're doing SLIM or inverse kinematics or teleoperation, we should be developing best practices following these guidelines. These practices will change over time as our technology improves, and especially our testing sets and our training sets will end up getting more and more complex and more representative of real world deployments. Well, I hope this has been a compelling come to Jesus moment. Please, consider the challenges of open world robotics. I do have a blog post on the topic if you're interested in more details of my philosophy on the subject. But I will leave it here and just thank my students who have done most of the work here, as well as my collaborators and the undergrad students who have worked on the TRINA project shown on the right here. Well, thank you very much. I'll take any questions.
Great. Thank you, Kris. The audience, if there are questions, please post them on Q&A and then we'll look at them and answer them. While people are writing questions, I have some, Kris. One question I had was I actually pulled up your listening to the heart and lungs paper. And I was wondering if, and you haven't done it, but in the next steps of this, whether patient experience is a part of the equation. Right, you had that nice graph of autonomy and supervisory control, and the distance between them is not that far, right? You can have a clinician sit there and do minimal work in terms of low-level control, but raise confidence in the patient that there's a human in the loop rather than an automated system. In making those decisions, what is your, what are your thoughts on how you balance them from the perspective of the patient?
So communication is incredibly important. It's really key to setting expectations and also making the patient comfortable with the upcoming procedure, especially in these semi-autonomous exams. Being able to set the tone for this is this kind of scary and foreign robot. You need to kind of prep them. This is definitely something that is a great HRI question. How do you get the person to trust that the robot's not going to hurt them? Of course, with experience of other people using this system and kind of over time, people will grow to trust these things more as long as the kind of the track record is good. And I think as tools, we already see. I actually had a X-ray exam that was basically done by a robot. I stepped into a kind of shell and this thing kind of spun around me, and I was given assurances by the human nurses that this was going to be safe. Now, that kind of initial communication is going to be key. They tell you to stand there, stay still, etc. Those types of prompts, I think, are the first line of kind of improving this interaction. The second thing is, we will need to have more research into adverse event handling with these robots. So certainly some fraction of people are going to freak out, or they're going to do some sort of unexpected reactions to the robot's movement. And this is a kind of application design problem. I think it's a pretty good one for industry to focus on, because it's going to have more impact at scale when you try to work with, let's say, hundreds or thousands of patients, rather than the folks who are just kind of joining your clinical study, which you can already prompt. So in the wild, I'm not sure exactly. I think it's a great set of questions for HRI, but prompting, reacting safely, and some degree of adjustment. Also, I think the speed of movement, studying how kind of these low-level movement factors affect people's reactions to close proximity robots is a really interesting and fascinating subject.
Mm-hmm. Great. I have one more question that I want to ask. I'm getting ahead of people, but in your commandments, you talked about listening to the users or contextualizing in what you learn from users. One of the things that we're finding in our work is that users who are kind of affected by the system are important to engage. In addition, we're finding that experts have a lot of knowledge, experts who used to or are performing these tasks that we're asking robots to perform, their knowledge, capturing their knowledge is actually sort of paramount to building effective systems. I was curious about what your experience has been working with experts.
So I guess maybe let me clarify. So you're saying that when you're trying to train people who are not trained, trying to train a robot using novices, I guess
So for example, the robot is listening to someone's lung, but a clinician does that. How do you kind of transfer the knowledge of the clinician to the robot effectively? Because clinicians are looking at lots of things, right? It's not just following a single trajectory. They're actually thinking about multidimensional things.
Yeah, that's a fantastic point. Yeah, so the way that we did it was we trained the sound quality regressor using trained clinicians who they know how to do auscultation. They gave a ranking from 1 to 10 about the kind of quality, about its diagnostic potential. So you have a 10-second sound clip. We trained a regressor to try to predict what the operator would, what a doctor would count on. So getting annotation from experts, getting demonstrations from experts is extremely important for trying to transfer that expertise onto the robot. There's tons of machine learning techniques for trying to do so. Experts, though, their time is very valuable, and that's actually been one of the limiting factors that we've found is that we can, I've also worked in ocular microsurgery, and getting an ophthalmologist's time to demonstrate something that we then record means that we're only going to get a handful of experience, and so we also have a kind of small data problem there because it's expensive.
Yeah, absolutely. So since we started a few minutes late, we can go for another few minutes. There's one more question. Let's take that, and then we'll finish up after that. Mike, you want to ask a question?
Oh, yeah, definitely. Yeah, thanks very much, Kris. Really interesting talk. I had a more specific question. So when you were talking about the informed teleop, the one for the open world robotics, where you have the unlabeled objects and try to provide assistance, I was curious, were the types of assistance that you had in that case discretely defined, or are you trying to infer about parameters or something else?
We're doing both the inference on the discrete choice of action, discrete parameters that might affect the action, and the continuous parameters that might affect the action. So for some of those, for some of the actions, it's sort of like a combined, it's a hybrid classification regression problem. And I guess some of the details of how we implement that, it's a structured prediction approach. It's basically, there's an enumeration of the kind of an auxiliary optimization. We're learning actually the scoring function for that optimization. We're learning the scoring function using a max margin style approach. And basically, the reason why that's great is because the optimization is the only part that's dependent on the open world perception part. So the perception module can provide any number of objects with any number of attributes, and the scoring will end up kind of giving a single scalar value to those. And so the auxiliary optimization is the one that's doing the hard lifting. Does that answer your question?
Yeah, definitely. I'll have to take a look at the details in more detail. One other, I guess, side question for that, was that just for constraints then, or were you also doing it for the impedance models or other interaction phenomenon?
So we didn't, in this case, have a knob to tune, for example, like impedance. It seemed like for these tasks, we were kind of focusing on the main kind of reorientation type behavior and constrained movement behavior for these sequential manipulation tasks. And so in this case, we had constraints turning on and off. All those were just binary variables, 6 degrees of freedom. You could turn all the constraints on or off. And we also had the selection of which plane you wanted to get to and how far you got from the plane. So essentially, if you look at a plane, the snapping action would kind of orient the hand towards that plane and also move towards a target a certain distance away from the plane. So this would basically be a preparatory move for later kind of frame-oriented moves, such as wiping, screwing, or kind of inserting pieces into a board.
Yeah, that makes total sense. Yeah, thanks.
Right. Thanks for the question, Mike. All right, let's wrap up and thank Kris. And it was an excellent talk. I'm really glad to catch up with everything that you've been doing. This is very informative for the audience. And thanks for agreeing to give us a talk, Kris.
You're very welcome.